The universe was supposed to be predictable. For decades, we've had a story of how everything came to be, a story that began with the Big Bang and the slow, steady formation of galaxies over billions of years. We built the James Webb Telescope to see the first chapters of that story, but instead it seems to have found a surprise ending written on the first page. What Webb has found staring back at it from the dawn of time isn't just surprising. For our old models, it's a challenge, and it's forcing us to reconsider what we thought we knew about the cosmos and our place in it. For nearly a century, our cosmic story was built on a powerful foundation, the Big Bang Theory, and its modern version, the Lambda Cold Dark Matter model, or Lambda CDM for short. This model has been a huge success, painting a picture of a universe that burst into existence 13.8 billion years ago and has been expanding and cooling ever since. In this story, the first 380,000 years were a blistering, opaque fog. Then, the universe cooled enough for atoms to form, releasing the first light, which we still see today as the cosmic microwave background. But after that, things went dark. The universe entered the cosmic dark ages. No stars, no galaxies, just vast, silent clouds of hydrogen and helium drifting through the expanding emptiness. According to the Lambda CDM model, the first stars didn't blink on until 100 to 200 million years after the Big Bang. These were the theoretical population 3 stars, giants made of pure primordial gas, hundreds of times more massive than our Sun. They lived fast and died young, seeding the cosmos with the first heavy elements. From those seeds, the first galaxies were supposed to grow, but slowly. The model predicted a bottom-up formation where small clumps of dark matter would gradually pull in gas to form tiny protogalaxies. Over billions of years, these infant galaxies would merge and collide, eventually growing into giants like our Milky Way. It was a story of slow, patient construction, a process that needed billions of years. Telescopes like Hubble showed us glimpses of this, and everything seemed to fit. But Hubble has its limits. To see the very first galaxies, we needed a new kind of eye. We needed an instrument that could capture faint, ancient light that had been traveling for over 13 billion years, stretched by cosmic expansion into the infrared spectrum. We needed a time machine. Enter the James Webb Space Telescope. With its massive 6.5-meter golden mirror optimized for infrared light, the JWST was designed to witness the cosmic dawn, the birth of the first stars and galaxies. When it opened its eye in 2022, the universe never looked the same. The first deep field image was a taste of the revolution to come. It was the deepest, sharpest infrared image of the distant universe ever taken. Using a massive galaxy cluster as a gravitational lens, it magnified the light from even more distant objects behind it. We saw galaxies as they existed over 13 billion years ago. But they weren't the faint, chaotic blobs we expected. Some of them were bright, shockingly bright, and that was just the start. As Webb continued its surveys, a consistent and fascinating pattern emerged. The telescope was finding galaxies that were far more luminous and substantial than our models had predicted. In early 2023, a team announced the discovery of 6 candidate galaxies seen just 500 to 700 million years after the Big Bang. According to the standard model, galaxies this early should be infants, but these 6 looked like giants, with estimated stellar masses of billions of suns. To get that big that fast, it seemed these galaxies would have to convert almost all of their available gas into stars with an efficiency that was thought to be impossible. It was like walking into a nursery and finding a teenager. The timeline didn't seem to add up. There just wasn't enough time in the standard model for such massive structures to form so quickly. The universe was supposed to be building with Legos. Instead, Webb found what looked like fully assembled castles. The most stunning example to date is a galaxy called JWST-GS-Z14-0. Confirmed in 2024, we're seeing this galaxy as it was just 290 million years after the Big Bang. At this stage, just 2% of the universe's current age, models predicted only the smallest, most fragile structures. Yet JADES-GS-Z14-0 is surprisingly large and incredibly luminous. More shocking still, astronomers detected oxygen. Oxygen is forged in the hearts of massive stars and released when they die. Finding it this early means multiple generations of stars must have already lived and died within that first 290 million years. A life cycle crammed into a time frame our models considered highly improbable. At first, scientists were cautious. Could they be misinterpreting the data? Estimating a distant galaxy's mass is tricky, but as more data came in, the core issue remained. The early universe was churning out large, bright, and chemically enriched galaxies far faster than anyone dreamed. The story of slow, patient growth was, at the very least, incomplete. While astronomers grappled with these surprisingly mature galaxies, Webb uncovered another stranger puzzle. Tiny, compact objects glowing an insistent shade of red. They've been given a simple name that belies their profound mystery: little red dots. Found in many of Webb's deep field images, these objects are common in the universe's first billion years. At first, some thought they were just another type of unusually massive, dusty galaxy. But the little red dots, or LRDs, didn't quite fit. They were extremely compact, almost like single points of light, and their spectra were bizarre. A new, radical idea began to take hold. What if these weren't just galaxies full of stars? What if they are powered by ravenously feeding supermassive black holes? In this scenario, an LRD is a young, growing black hole shrouded in a thick cocoon of gas and dust. This dense shroud would explain their red, compact appearance and why they often don't show the strong X-ray signals typical of feeding black holes. Recently, astronomers using NASA's Chandra X-ray Observatory may have found a crucial link: an LRD that is emitting X-rays. This object, cataloged as 3DHST-Aegis-12014, might be a transitional phase where the black hole has begun to blow away its gaseous cocoon, allowing X-rays to escape. This suggests LRDs could be a specific short-lived phase in the growth of the first supermassive black holes, a phase we've never witnessed before. This discovery is a double-edged sword. It might help explain some of the impossibly bright galaxies by recategorizing them as active black holes, but it opens up an equally profound mystery. We are witnessing a major revision of the first chapter of cosmic history. This is science happening in real time, with new data challenging our models almost daily. As scientists around the world race to unravel these puzzles, make sure you're subscribed and have notifications turned on. You won't want to miss the next update as we explore this new, unimagined cosmos together. The problem of supermassive black holes has been a quiet puzzle in cosmology for years. We see them at the center of nearly every massive galaxy, including our own, behemoths with millions or even billions of times the mass of our Sun. The question has always been, how did they get so big, so fast? According to standard models, black holes grow by pulling in gas and merging with other black holes. But there's a physical speed limit to how fast a black hole can feed. Even if it fed continuously at this maximum rate, it's incredibly difficult to explain how billion solar mass black holes could exist less than 1 billion years after the Big Bang. It's like trying to fill an Olympic-sized swimming pool with a garden hose in under an hour. It just doesn't seem to work. Cosmologists proposed a solution: heavy seeds. Instead of starting from a single dead star, perhaps the first black holes were born from the direct collapse of massive primordial gas clouds, creating seeds that were already tens of thousands of solar masses. This would give them a huge head start. The little red dots might be the first observational hint of this process in action. If they are indeed young black holes wrapped in dense gas, Webb could be showing us this heavy seed population at the very moment of its rapid growth. We may be witnessing the birth of the monsters that would come to dominate galaxies for the next 13 billion years. Unexpectedly bright galaxies, mysterious red dots, and monster black holes born too soon. Each of these discoveries is a fascinating puzzle. Taken together, they represent a significant challenge to our standard model of cosmology. Let's be clear, this doesn't mean the Big Bang is wrong. The evidence for an expanding universe that began in a hot, dense state remains overwhelming. What's being tested is our understanding of what happened after the Big Bang. The Lambda CDM model, the set of rules we wrote to describe how galaxies and other large structures formed, appears to be incomplete. The situation is pulling our understanding in multiple directions. On one hand, Webb's data has sharpened a long-standing problem known as the Hubble tension. Its precise measurements confirm that the universe appears to be expanding faster today than models based on the early universe would predict. This might point to a new ingredient in the early cosmos, something often called early dark energy. On the other hand, to explain the rapid growth of galaxies and black holes, scientists are exploring adjustments to the physics within the standard model. Things like how efficiently stars form, how they enrich the cosmos with new elements, and how dust behaves in the early universe.